Thank you, Chairman, for your kind introduction, and also thank you very much for attending the talk. First of all, I'd like to thank the organizer for inviting me to give a talk today, and I'll discuss about photodetector made by organic semiconductor materials, which is essentially a material that's very suitable for flexible electronics. And then I'll discuss about the application. So this is the outline of the talk. First of all, I'll give you a quick overview of different types of organic photodetector, or in general, organic sensors. And then I'll discuss a very interesting application called a multispectral photodetector. We've heard a lot of antenna work throughout the day today. And in the antenna system, there is also an organic sensor, not necessarily organic, the sensor. Sensor basically converts the light signal to electric signal. And most of the sensors, they are broadband. The response to electromagnetic waves cover very broad wavelength range. So when you work on specific detector, you need to tune the detectivity at a particular wavelength range. For example, very often you use so-called color filter or filter. But the moment that you use the filter, first, it adds on the cost. And it's not very good approaches for flexible wearable electronics, because the filter essentially is a thin film interference effect. And once you band it and then lost filtering performance. So really the work is that how we'll be able to use a semiconductor material response to a broadband wavelength range, be able to detect, achieve the function with a specific wavelength range without using filter. That's the idea. And then I will propose two techniques or device architecture developed by our group called tri-layer photo modification organic photodetector and double heterojunction structure. Then I give you some examples of how this multispectral organic photodetector can be applied in various applications. Then I'll give you some examples of applications. We know that the electromagnetic waves in nature essentially covers very broad wavelength range. Human eye essentially is a detector. The wavelength range that we can detect covers, say, wavelengths from 400 nanometers to 750 nanometers. That's that range of the electromagnetic waves that we define as light. So with different colors that we says. But there are other things that are really beyond detection of human eye, beyond our detection detectors. For example, near-infrared wavelengths, near-infrared light with wavelengths of slightly beyond the radius, the wavelengths that we can detect. So therefore, in order to detect the range of electromagnetic waves beyond a human vision, then we use photodetector or optical detector to help us to extend our vision. For example, we use near-infrared detector for night vision application for thermal therapy, bioimaging, telecommunications. There's a ranges of technology that they can use for apply various photodetectors. So the photodetectors, we heard about UV detector this morning, zinc oxide nanowires, visible light, near-infrared light, or mid-infrared. Depends on the materials, the type of materials that you use. Essentially, the material that responds to a certain range and then we build into the devices that the resulting photodetector has the corresponding photo detection, spectral detection wavelengths. For organic semiconductor made by a carbon-based material that can be prepared by solution fabrication. It's very suitable for large area, flexible devices. This class of organic semiconductor materials has attract a lot of interest for photo detect application because the nature of the photo response of these semiconductor materials can be tuned from visible wavelength range and extended to the long wavelength range part. It's very suitable for making near-infrared photodetectors. These are the materials. organic semiconductor materials with the band gap tuning depending on the structure of the material molecules over the range from 1 to 3 electron volts that covers many things. In the past, one of the projects we did in our group is using as a flexible OAD, and you can also use the organic semiconductor for making flexible circuits, TFTs, etc. And FID, we heard a lot. So one of the properties of this semiconductor materials is that they have a very good a broad optical sensing property. They can be used for different types of devices, transistors, light-emitting diodes, and sensors, and on the flexible substrate, of course, solar cells as well. So today I'm going to discuss about the organic photodetectors that enable us to have a dual detection functions and how they can be used and the application. So a few years ago, we wrote a review article, was invited to discuss about the solution processable organic photodetectors on flexible electronics. We summarize that there are 3 types of photodetector. One is a photo transistor. This is 3-terminal devices, 2-terminal photoconductors, and also photodiode. There are pros and cons for organic thin film transistors. This particular materials, the sensitivity of the sensor is very much dependent on the molecular packing or the morphologies of molecules in the channel layers. So there are ways to control the molecular capping such that to enhance the photo responses. The advantage of this is that you can make a photosensitive transistor in a very small sizes, still with a very high photo responses. It'd be very good for miniaturize, very fast response. Well, for diodes, we heard talks today that using sensors or using for antenna applications, using solar cells, and so this type of device be very easy to fabricate. The 2-terminal devices, essentially you have a stack of organic semiconductor materials sandwiched between the front contact and the rear contacts, and the light will generate the current. So external quantum efficiency of photodiode or organic photodiode typically is less than 1%, 100% less than a unit. While recently developed the so-called photo multiplication type of organic photodetector, 2 terminals with external quantum efficiency way beyond unity. So this is something that's very interesting and hot in the topic I'm going to discuss in a moment, and very simple device architecture and possible for multispectral detections. So this is the cross-sectional view of an organic photodiode. Essentially, you have a bulk heterojunction because you have a positive or p-type or n-type of materials blend together and of polymer acceptors to form a bulk heterojunction, a sandwich between cathode and anode with electron transporting layer and hole transporting layer to assist the collection of the charges. In general, I mentioned that response of a photodetector, whether this is a semiconductor, inorganic semiconductor materials or organic semiconductor materials, it depends on the nature of the absorption properties of the material that you use. In general, it is a broadband responses. That's what the sensor optical sensor devices to use. There's another type of a material, we call the photo multiplication type effect, PM. In organic solar cells or sensors that we heard from the speakers present today, usually they are so-called photovoltaic effect, like solar cells. So external quantum efficiency of that type of detector is less than 100%, or in other words, for every electron hole pairs, the device generated per incoming photons. So usually theoretically, the limitation is for every incoming photon, you could only generate one electron hole pairs or one electron. Therefore, this is less than one. But in organic semiconductor materials, typically polymers or acceptor materials or donor or acceptor materials, when you blend them together, the underexposed of the light, exciton generated. Exciton is excited states, or in other words, is a pair of electron hole pairs. The electron hole pairs need to decompose at the donor-acceptor interfaces. So if you reduce say, for example, the concentration of N-type semiconductor materials, and then as the concentration decreases, then originally the balance between the hole and electron dissociation does get lost. So in other words, the electrons we may not be able to find percolation pathway to the photo-generated electron may not be able to be extracted efficiently. So therefore, they left over in the whole active area we call the bulk heterojunction, because the less proportion of the acceptors. So therefore, the exciton or the excitons can only be dissociated at the donor-acceptor interface. If the acceptor concentration is extremely low, holes can be extracted out efficiently, but without electrons. So therefore, these acceptor becomes the traps in the semiconductor materials. So it becomes in the absence of light, these acceptors becomes the traps, and therefore, if you apply a bias, you could hardly generate a current because of the poor conductivity of the materials. But in the presence of light, and those trapped will trap electrons, photoelectrons. So in organic semiconductor materials, the charge carrier concentration in organic semiconductors is relatively low in the absence of light. And all of a sudden, in the presence of light, because of the traps, trapping the photo-excited charges, therefore to create a bending effect because of a sudden increase in the charge concentration. So therefore, because of tunneling effect, allows the charges to be injected through the system. So this is not a photocurrent, but it's induced by the photoluminations. So according to the definition, number of electrons injected or the current divided by the number of photons, the ratio will be way above 100%. So therefore, this is called a photomultiplication effect. This is very interesting and useful. So based on this concept, then I'll introduce another idea. How are we able to create a multispectral photo detection using single photodetector without incorporating a filter in the systems? So as I mentioned that most of the organic semiconductor materials, they're broadband. For example, if I select one particular set of systems that will respond from 400 with a spectral response from 400 nanometers to say 650 nanometers. This is one, if I call this material is absorber one, absorbs the incoming light over the wavelength range from 400 nanometer to 600 or 620 nanometers. And then I select another set of a material system, which if I define absorber two. Absorbing materials, absorber two covers the photo response from 600 nanometer all the way to, say, for example, 800 nanometers. Then what happens is that if you stack the two materials together, if the device is designed properly, and you can do it in such a way that for incoming photon with wavelengths below 620 or 650, all being fully absorbed by the first layer, and only left over the longer wavelength portion of the incoming light, which cannot be absorbed by the first absorber, then be penetrated, captured by the second absorber. So in this way, you will be able to detect the incoming light selectively, depending on the choices of the material combination that you use. So in this case, is that, for example, as an example, we use absorber one that only sensitive to the visible part of the incoming light, and select absorber two, with the absorption extending to near infrared light. So if you design properly, the visible portion of the incoming light will be fully depleted by the first layer, whereas the leftover things will be long wavelengths will be selected, absorbed by the second layer. Now, this is very interesting. So if you apply a bias and the forward bias, it will generate a photocurrent. And the photocurrent will only due to absorption of incoming visible light or depending on the incoming near infrared light. So therefore, you'll be able to selectively detect the light accordingly. So first, we apply bias across, do a quick simulation. You will find that when you apply a forward bias, say reverse bias first, then this is the photo response behavior. According to the simulation, you will find that this interesting structure, when you apply a reverse bias, you see a photocurrent primarily contribute from the absorption of the short wavelength portion of the incoming light and the long wavelength portion of the light. If you apply a forward bias because of this multiplication effect, then you have this type of photo responses. That means most of the visible portion of the light will be fully absorbed by the front contents portions of the organic semiconductor materials. Now, the idea is that whether you'll be able to define or design the devices properly such a way that the visible part of the incoming light will be fully absorbed by the first part, whereas the long wavelength part will be fully absorbed by the rear part in such a way that you are able to detect selectively the visible light and the infrared light simply by changing the priority of the voltage applied across the devices. That's the idea, but you need to do some careful simulation. So with the concept idea, then we introduce a third layer called a spacer. The idea of the spacer is to deplete the visible light such that only allows the long wavelength portion of the incoming light can be captured by the second absorber, although the second observer also has the capability to absorb short wavelength light. But we design it such a way that let the incoming, the visible part or short wavelength portion of the incoming light fully depleted, absorbed by the first layer. So doing this, then that will be very good. You have the so-called dual mode. So this is the design, final design. This is, by the way, this is a solution processed multi-layer. So we select 460 nanometer. You will find that the 460 portion, the visible portion of the incoming light is fully absorbed by the first absorber. And with the use of the spacer, then it's fully depleted. So no visible light is entering into the second layer. Whereas the long wavelength portion of the light, because it does not absorb by the first layer, then it penetrates through and then absorbed by the second layer. So this is very interesting. Now, if you apply the reverse bias, it will generate a photocurrent. And this current is due to the absorption of a near infrared light portion of the incoming light. So under reverse bias, this device generates photocurrent. And you know this photocurrent is due to the absorption of the long wavelength portion of the photon. And near infrared at the short wavelength or the visible portion of the incoming light does not absorbed by the first one, but does not generate a photocurrent because if it's under reverse bias, the Fermi level of the front contact and the LUMO level of the organic semiconductor or conducting band, if you like, is too large. So it is difficult to inject the current. And at the same time, if you apply a forward bias, then the interesting things happen, it's reverse the effect. Because under forward light, then you are talking about injecting electrons from the cathode to the LUMO level. Because of the high interfacial barrier, it is difficult to generate a photocurrent. Because under forward light, forward bias, the absorption of the incoming light induce a lot of trapped electrons. Therefore, the tunneling occurs at the interfaces, in the front interface. So under forward bias, you will also be able to generate, measure the photocurrent the induced current, but the current is due to the absorption of the visible light. So therefore, you're able to detect visible light and the near-infrared light selectively by changing the polarities of the bias across sensors. This is the first type of this kind of things that we developed. So for example, if you apply forward bias, the dark curves is the dark one is the dark curve, the black one is the dark curve. So in the forward bias, only visible light will be able to generate a current. If you apply reverse bias, in the presence of visible light, it does not generate any photocurrent because the visible light is fully depleted by the first layer. Vice versa, if you apply forward bias, even in the presence of NIR light, it doesn't generate a current. It's just like a dark devices, the dark curve, because it doesn't generate a current. So it only works in the reverse devices. So this way, we generate such an interesting phenomena called, maybe I need to move faster a bit. So on the forward light, in the presence of ambient light, if you decided to detect a visible light or near infrared light, and then all you need is change the polarity. Now the concept of this is very general. By changing the materials, then you'll be able to do the detection in red light, blue light, for example, or NIR1, NIR2 for biological applications. And this has a very good linear dynamic range. So we also introduce another concept based on the same devices. We know that the diode, so photodetector basically is a photodiode. Yeah, in the if you have a two thin film monolithically integrated photodetector, same idea. One responds to a broader wavelength range. The front one responds to the slowly narrower responsive wavelengths. When you add them together, you apply a bias. If it is a positive bias, one of them will be operated under reverse bias. That means that depending on whether this is long wavelengths or short wavelengths, so it only detects one portion of the incoming light. So the same concept also applies to visible light. So it depends on the material that you choose. For example, in this particular work, we select the first absorber absorbs the blue light. The second absorber absorbs the red and green light. So when you apply a positive bias, this whole thing only detects the blue light. If you reverse the bias, this detects the green red light. This is something that's very interesting. And so in order to demonstrate the potential application, then we look at the application site. The first one is to look at the dual channel optical communication. We all know that this ASCII code, 26 alphabets, letters, and each letter has its unique code. For example, CAT. C has a 0110011, for example, code, and A, and etc. So we apply this coding using visible light. That means encoded signal. At the same time, we generate a signal using functional generator, generate a signal with a DOG, for example, with different code. But this is encoded within an NIR light. And we merge two light beams together, broadcast. And then you use detector to detect. If you're using conventional broadband detector, silicon detector, then you receive the mixed signal because a silicon detector detects a visible light and near infrared light. And the silicon detector cannot distinguish whether incoming photon is a short wavelength, visible light, or red or green, or it is near infrared. It just generated a current. So you cannot recognize different. But in this case, is that organic photodetector, it depends on the polarity. If we apply the reverse bias, then this detector doesn't recognize the visible light. We call this a visible blind, or otherwise it becomes near infrared blind visible detector. So you'll be able to see decoding very easily. And this another example, just now I mentioned the blue and the red. So I found that this was the purpose, of course, for demonstration. Faculty of Science at the Baptist University has a logo with a molecular orbital. One is a blue color, one is a red color. So I purposely select this, I put on the step motor and shining with a white light and using sensor. When the sensor is operated under forward bias, it only recognize or detect the blue portion in the testing object. Then we switch to reverse bias, that only detects the red light, the long wavelength part. So you can selectively detect. So therefore we define, this is very interesting and useful, self-aligned imaging in distinctive bands. So you are measuring an object, for example, biology tissues, and with different components, each responds to a different absorption in a certain or maybe in distinctive wavelength range, then you could use to mapping, produce a mapping. You can combine them together, then you do the same setting for the organic sampling. And there is another work we did to demonstrate that this is a piece of artwork prepared by artist Georges Seurat from France 140 years ago, and very famous because this is made by pointillism. We know that Western painting usually is by brush, but this is a so-called pointillism. And if you zoom in, look at this picture very carefully, it was produced by the dots, right? For example, this lady had a very beautiful purple dress, but at that time, 150 years ago, purple color could be very expensive. The artist at that time was very smart. And the Georges Seurat used very fine points, blue dots and the red dots put side by side. And our mind, our human eye has a spatial resolution. That's some kind of fake imaging. If you place the two different colors close to each other, and then our mindset will see the combination of the two different colors as a third separate color. So you see that if you see this picture is a purple dress, but actually there is no purple color inside. It is just a dot of red and a blue. It just if you see from distance, then becomes so this is a perfect example for us to duplicate the work to demonstrate the sensor. So this is the response of the human eye, the retina. We have a red, green, and blue. The consensus on the retina, and this is the bias controllable sensor with different colors. So we use the two sensors, be able to detect 3 different colors. One sensor works for blue and green, red. And because at the moment we cannot differentiate red and green because of the 2 bands. So therefore I use another green band filter to filter out the red one so we can duplicate RGB 3 color. Same story. We can scan the red, green, and the blue, use 2 sensors. So in future, if this technology could be applied, eventually you can use 2 sensors for generate RGB or even further. And one of the ongoing work that I'm working on is whether it's possible, 1 sensor be able to detect red, green, blue, 3 colors by changing the priorities. Then your mobile phone in future, RGB, you don't need to have 3 sensors, pixels. 1 pixel does the full color. Then as you can imagine, you can have a super high resolution display in future. Yeah, this is very useful for machine vision because in certain cases that it is difficult for human to work in very hazardous or dangerous places. For example, if there is a fire, and then you can send robots in, and with the machine eye, one responds to near infrared, the other one is visible. So visible light, you can see the frame, and the near infrared see whether there is still life inside. That would be very, very useful. So we duplicate it, and this device is using multispectral sensors. So for example, if you apply reverse bias, you see the long wavelength portion. So same object as I mentioned that if you take imaging,
and then you see the near infrared or long wavelength portion of the images that provide you one information. If you switch to visible wavelength range, you see the visible portion of the images. If you apply a square duty cycle, then you see the whole range, broad band wavelength range. I use HK reverse for near infrared, BU Baptist University. I could also use a Tang University as well, if I could have a project with the collaborator. Now, the other application that I would like to highlight today, since I have 10 more minutes to work, I'll give you another very recent work to see how flexible or organic electronics devices will be able to do something that can be relevant to our daily life. In Hong Kong, it is very popular. You send a message through your mobile phone and order a pack of fruits and deliver to door. Right? And very often that sometimes can be quite frustrating. When you open a box of fruits, maybe 80% of them are right, and the rest of them are either spoiled or they are not ready, but not very sweet. So open a box of fruit is more like a magic box. Try your luck. Yeah, it's not always predictable. So one of the reasons that there is no consistent quality control information, or in other words, there is no traceable food quality information that's available. When we talk about a food quality, essentially is talking about the sugar acidity level, water level. Yeah. The reason that I'm interested in this is because of the near infrared photodetector, because glucose molecules, sucrose molecules, for example, represent the sweetness level of the fruits. These molecules, they have several characteristic absorption peaks in the near infrared wavelength range. So in other words, even if the fruits are still on a tree, and in the day, Sunday, like these sunny days, is it possible to monitor the sugar content? Basically, it's the absorption of the near infrared light by those glucose molecules in the absence of ambient light. So the conventional silicon photodetector, for example, just can't do it, because whatever the things you get give you a lump sum information, covers everything. This is a wrong mode, right? But if you're using so-called visible blind, or maybe wavelength selective photodetector, that would be very interesting. So one idea is that, is it possible to monitor the changes in the glucose molecules in the fruits from cultivation, harvest, and the quality control in the market level? How will we be able to do that? Actually, it can be done, because fruit is a huge market, and there's a lot of fruit waste because of fruits they will pick up not at the best season, best time. So the idea is that glucose molecules, they have a feature absorption peaks in the near infrared range. Now the idea is that if we develop, these are the absorption peaks, near infrared absorptions of those fruits, grapes, peaches. We've done a lot of fruits. And this is the small detector that we developed with the near infrared light sources. Since the sweetness level of the fruits can be predicted and monitored by precisely determining the changes in near infrared wavelengths by the concentrations of the sugar molecules. And all you need to do is do a setup like this. And then we did a test. It would be very interesting. We pick 3 different types of fruits. Grapes, for example. It just happened that in the market, I would just randomly pick 3 different species of grapes, but actually they look very similar, but I didn't realize that time there's a number of them, and pick all of them and measure the near infrared absorption spectrum of each of them. These were represented by the blue dots. That means I buy a whole box of grapes and measure near infrared spectrum of each of them and juice them and measure the absolute sugar content in the grapes that I measured, so that I generate a database, the blue dots, and then send the signal to cloud, because of big data, because each blue dots refers to one spectrum and absolute sugar value, so that I can use algorithm to predict the sugar, and the near-infrared absorption range. And the red dots are the ones that you pick randomly from the market. So long as the sweetness level is within the tester range, then you'll be able to do the quick match immediately without destroying them anymore. So I also did authentication, the full. This is interesting. If the 3 different types of the fruits, grapes, and I pick 50 of each of the species and do the measurements, and using the same technique that the previous speaker mentioned, and the accuracy rate is more than 90%. Can precisely predict which species of the grapes, because each grapes will have a different difference in their infrared measure. So this is the prototype that I developed. Our group detector you can use for measuring grapes, measuring tomatoes, measure for apples, and we developed the app you can download and then do the quick measurement. The idea is that you do the scan and upload the data to the cloud, because the algorithm is also stored in the cloud, and do a quick pair, and then it tell you what is the sweetness level, what type of fruits that you made. Because of time, so I do not run this, because I have a project I have to demonstrate this. So this is called a minimal viable product, so that I can deliver the project. So this is the summary. In general, the photodetectors are broadband. You cover a wide range. One of the aim is that we develop an organic solution processable semiconductor that provide you a very broad wavelength. And the second idea is that using the so-called absorber 1, absorber 2, and then depending on the distance between the absorption edges of the absorber 1 and absorber 2, and you can have a narrow band or you can have a dual band. And currently we're working on the multi-band, so that you'll be able to do the same detector, you do a lot of interesting detections. So the idea is that if you are able to do the multiple measurements, and you realize imaging and monitoring different things in the different bands, and the visible blind NI detector for precise, rapid, stable, traceable measurements. Currently, we're working on the fruits. And my students are the happiest ones in Hong Kong, probably not just in my university, because they are asked to do the biological test of the fruits every day with different species. I actually brought the project to attend the Geneva International Convention last year, and this work won the gold medal. So I was quite pleased to take an opportunity to present you the work. Yeah, for that, I would like to thank my students, all the ground support, and thank you for your attention.